Okay, we're back. We're talking about speculation and speculation to speed up a single program. And I'll cover two techniques that were proposed to do this. One is slipstream processors. Slipstream processor is an interesting technique. Basically, the goal is similar to many thread-level speculation approaches to use multiple hardware contexts to speed up single-thread execution. This is also called implicit parallelization, right? Implicitly parallelize a program. The idea in slipstream is to divide the program execution into two threads, the advanced thread and the redundant thread. The advanced thread executes a reduced instruction stream speculatively, and the redundant thread uses results, prefetches, predictions generated by the advanced thread and speeds up using those results and ensures correctness. Redundant thread basically executes every single instruction, but it executes it faster because the reduced instruction stream provides some execution hints to the redundant thread. That's the idea. The benefit is by having these two threads, execution time of the overall program actually reduces. So the core idea is similar to many thread level speculation approaches, except the key point here is to have a reduced instruction stream as the advanced thread. So with the speculative parallelization prefetching method that we've discussed earlier, pre-execution method, it's very similar to that method. There you can have a reduced instruction stream as well. This is also similar to multiscalar, except multiscalar doesn't reduce the instruction stream, if you remember. Thread level speculation that we talked about earlier from Stefan et al., they don't reduce the instruction stream. Here, instruction stream is reduced, and it's reduced dynamically. And we'll take a look at how it's done. And this paper talks about slipstream processors improving both for performance and fault tolerance. It actually discusses how we can improve fault tolerance as well, right? Because if you redundantly execute instructions earlier in a reduced thread in some other processors, for example, you can try to when you redundantly execute the instruction, you can check whether the execution actually matches or doesn't match, and you can achieve some kind of fault coverage by this kind of redundant execution of instructions. Okay, slipstreaming, the name comes from actually an interesting thing, one of those NASCAR or Formula One races, right? If you're a car racer, you would know this. Basically, this is from the paper, and this is a really nice analogy actually, because what you really have is one thread, one processor, one hardware context executing fast, and it's pulling this back slower hardware context such that it also executes fast at the same time. And this is the notion of slipstreaming, and basically what happens is at speeds in excess of 190 miles per hour, there's high air pressure that forms in front of a race car and a partial vacuum that forms behind it. This creates drag and limits the car's top speed. A second car can position itself close behind the first one. This is called slipstreaming or drafting. Now this fills a vacuum behind the lead car, reducing its drag. Now the lead car can go faster as a result of this. And the trailing car now has less wind resistance in the front. And by some accounts, according to the paper, the vacuum behind the lead car actually helps pull the trailing car. Now the trailing car actually can move faster also. As a result, both cars can speed up by several miles per hour. The two combined go faster than either can alone. And that's the idea of slipstreaming, basically. This front processor, the advanced thread, can go fast and pull the slipstreaming, through slipstreaming can pull the thread that's the redundant thread by generating results for it, prefetches, branch predictions, results, values. And as a result of these values, the back thread or the redundant thread can go fast. And once it goes fast, it figures out whether the advanced thread is doing something wrong or not, right? So it can figure out it can synchronize with the redundant thread early on, advanced thread early on, such that advanced thread doesn't go into the weeds. Okay, so this is a nice analogy over here. Basically, slipstream processors detect and remove ineffectual instructions and run a shortened effectual version of the program or the advanced A stream in one thread context, and they ensure correctness by running a complete version of the program, redundant or R stream, in another thread context. Shortened A stream runs fast. R stream consumes near perfect control and data flow outcomes from A stream and finishes close behind. The two streams together lead to faster execution by helping each other than a single one alone. This is one possible hardware over here. I'm not going to go into this in a lot of detail, but this could be a multi-core engine. This is one core executing the A stream. This is another core executing the R stream. Basically, advanced stream what happens is advanced. There's a predictor, redundancy predictor, and redundancy detector that figures out which instruction should actually be executed by the advanced stream. Advanced stream executes those instructions, puts them in a delay buffer, and redundant stream takes them out of this delay buffer and re-execute every single instruction, but it basically reuses the buffers, reuses the results coming from the delay buffer. And advanced stream fetches data into the L2 cache, and R stream can actually read data from that L2 cache. In this case, this is an old paper, but it talks about R stream state only, but it's actually, you can actually fetch data into the cache such that R stream's caches are warmed up by the time it gets to the instructions that's needed. So that's the basic idea. You could do it in a multi-threaded context. You could do it in a multi-core context like this. So the key question is, how do you remove instructions in slipstream processing? And this is actually a tough part of the slipstream processor. Basically, this IR detector detects ineffectual instructions and conveys them to the IR predictor. Ineffectual instructions are dynamic instructions that repeatedly and predictably have no observable effect. You would really like to remove that. For example, if a store is unreferenced after a point, you would like to remove it. And why could it be unreferenced? Because of compiler optimizations, right? So you can move the store somewhere before a branch, and you take the branch, and the store may not be needed here, right? It may really be needed on this path, right? But compiler optimization may move the store, hoist the store up there for some reason, right? Non-modifying writes, for example, if you have a silent store, if the store is writing the same value, that's an ineffectual instruction. You can remove its dependence chain also, backward dependence slice. Dynamic branches whose outcomes are consistently predicted correctly, these can actually be removed also, because you have the redundant stream to execute when you do the wrong thing, right? So a lot of loop branches and the instructions that are feeding those loop branches can be removed from this advanced stream, right? And the removal happens from the R stream instructions, right? IR predictor, basically this IR detector operates on the redundant stream, but IR predictor, when the A stream gets to a program counter, IR predictor says, oh, you should not execute it because these instructions are ineffectual, right? That basically removes the instruction from the advanced stream after repeated indications from the IR detector. There's some confidence mechanism. You can read the paper for more detail. But basically, A stream, advanced stream, skips these ineffectual instructions and executes everything else and inserts their results into the delay buffer. R stream executes all instructions but uses results from the delay buffer as predictions such that it can speed up. So what if A stream, one question with this kind of mechanism is, what if A stream deviates from correct execution? You can actually have a wrong prediction, right? In the advanced stream, because A stream may incorrectly remove some instructions, or it can access some stale data in the L1 data cache that's not updated, right? How do you detect it? Basically, there can be a blanch or value misprediction that happens in R stream, and this is also known as instruction removal misprediction. And once this misprediction is actually detected in the back processor in the R stream, redundant stream, because redundant stream, remember, it's there for safety. It's really there for correctness, whereas A stream is really there for performance. Remember, we covered token coherence that decouples performance and correctness. We're really decoupling performance and correctness somehow here. The redundant stream is ensuring correctness. The advanced stream is ensuring high performance by prefetching results, by generating results for the R stream. How do we detect it? Well, basically, when on the R stream branch or value misprediction happens in R stream, at that point, A stream register state needs to be restored by copying values from R stream registers using the delay buffer or shared memory exception handler, and you can read the paper. And A stream memory state needs to be restored also, and the paper discusses one method of doing this, but there are other efficient methods. So you can imagine that the speculatively written blocks by the A stream should not really get communicated to the R stream if they're really wrong, right? R stream basically needs to access memory to get the correct data. So basically, A stream memory state needs to be restored somehow. So there are several questions in slipstream. How do you actually construct the advanced thread, and how do you speed up the redundant thread? The original proposal of slipstream was limited, in my opinion. Basically, it dynamically eliminates the redundant instructions, silent stores, and dynamically dead instructions, and dynamically eliminates ease to predict branches, which is good, but it leads to some complexity for this elimination. But there are other ways. You can dynamically ignore long latency stalls, just like run-ahead execution does, right? When you get to a long latency cache miss, you ignore it and you keep going. This way you can create an advanced thread. And remember Sun Rock processor that we discussed in the multi-core lecture? That's essentially what they did in a sense, right? You can think of that as an advanced thread and a redundant thread. And that's what they called it, right? You have an advanced thread that dynamically ignores long latency cache misses, in that case L1 cache misses, A thread. And you have an R thread that basically executes, this A thread executes instructions that are independent of the cache miss, and the R thread's job is to execute instructions that are dependent on the cache miss. So this is another speculative parallelization approach, Sun's Rock processor, right? We've already covered speculative parallelization with Sun's Rock processor. Their goal was to tolerate memory latency better. And the way they did it was through the advanced thread and redundant thread. That's very similar to slipstream, but advanced thread and redundant thread are constructed differently, and also they execute different instructions. So redundant thread is really not fully redundant in Sun's Rock, because it executes only the deferred instructions. So you really partition the instruction stream into two in Sun Rock. That's the main difference between slipstream and Sun's Rock processor. They call it the simultaneous speculative threading. Yeah. Simultaneous speculative threading. And I'd encourage you to read the Sun paper if you'd like to get more information. So you could do this that way. Or, let's go back to slipstream. Other ways is you can statically construct an instruction stream that's based on profiling, and that's based on some execution, right? That way you can reduce the size of the code that gets executed in the redundant stream. And there's a paper that I would recommend you to read from Rochester, a performance correctness explicitly decoupled architecture. If you're interested in doing research in this area, explicitly decoupled architecture. They use a compiler to construct the advanced stream, and that way they can actually make the advanced one of the processors simpler as well. And this was published in Micro 2008. I believe it's Alok Garg and Michael Huang. Garg and Huang. You can take a look at this paper. Okay. How do you speed up the redundant thread? That's another question, right? Original proposal actually reuses instruction results, control and data flow outcomes from the advanced stream. It turns out this is not that easy because you need to merge the results into the redundant stream, right? Somehow, and the redundant stream is executing out of order. How do you actually merge the results coming from the advanced stream into the redundant stream if you would like to do that? There are other ways. You can only use branch results, for example, to simplify things, or prefetch data as predictions. So original proposal actually didn't evaluate the impact of memory because memory latency was very short in the evaluated architecture over there. So if you'd like to actually look at there are a lot of issues in reusing some of these results, and I'd recommend one of the papers that we have written in IEEE Computer Architecture Letters about reusing the results of pre-executed instructions in a run-ahead execution processor. So this can tell you some of the issues in reusing the results of pre-execution with a specific case of run-ahead execution processor. And you know about run-ahead execution, and a lot of the concepts are similar, right? So run-ahead execution has a thread that's kind of looking forward, and that also can generate results, and that can actually, those results can be used by the main thread, right, instead of just the data values. Now it turns out it's difficult to do this, as explained in this paper, because you need to merge the results somehow. It's also not that effective because once you these results that are actually generated by the original thread or by the run-ahead thread, if you will, are actually for those instructions that are not necessarily on the critical path. The instructions that are on the critical path are actually dependent on the cache misses, right? Because cache miss takes much longer. So these instructions, reusing the results doesn't help that much in terms of performance, but it helps in terms of energy. Right? So it may be more interesting to actually design slipstream processors that actually where the advanced thread actually prefetches data for the redundant thread, and advanced thread also enables execution of mispredicted branches in the redundant thread in a more accurate way. So that brings us to something called dual core execution. Dual core execution is a similar approach to slipstreaming, except it designs the front processor and the back processor, or advanced thread and the redundant thread, in a different way. The idea is you have one thread context that speculatively runs ahead on load misses and prefetches data for another thread context. That's the front processor basically gets ahead of the back processor by not stalling on cache misses. That's the key idea. So if you look at this, you have two cores. In this case, it's like a chip multiprocessor. A superscale out of order core, superscale out of order core here. You have an in-order fetch. Basically, this front processor is like a normal processor. It doesn't skip instructions, but what it does is it does run-ahead execution on long latency cache misses, and all of its results are put into this result queue. If run-ahead execution is done, instructions that are dependent on L2 cache misses are not executed, and they're just placed into the result queue to be executed by this back processor. Back processor takes instructions in the order that comes from this result queue, basically in the dynamic execution order that has happened over here. It basically re-executes instructions, and it also executes instructions that were not executed because they were dependent on cache misses. It basically checks the result of every instruction correctly, one by one, and eventually retires the instructions over here. And if there's a mismatch between the execution that happens over here and the execution that happens over here, this back processor is the correct execution, and there is a flush that happens and instructions, the entire processor gets redirected. So the pipeline is a bit longer, if you will. This feels like a new pipeline stage in front of this back processor, because back processor now gets instructions from here. But now, if you have long latency cache misses, you can do run-ahead execution on them over here, and you can still keep executing independent instructions and keep feeding them into this result queue. And you can really have a very large instruction window, if you will, because this result queue is really a FIFO, right? It's a first in, first out queue. And you can scale its size to be much higher. Your processors don't need to be that large. In fact, they could potentially be in-order cores, right? They don't need to be superscalar cores. But basically, this result queue enables the look ahead of the window to be very large, because all of the instructions window in the window are all of those that are decoded by this core, until all of those and all of the instructions that are decoded by this core and they're executing in this cores are included in the window. These instructions that are sitting in the result queue are included in the window, and there are a bunch of instructions that are in the window of the back processor that are being executed. So they're also windows. So you can actually have a very large instruction window by decoupling these two processors that way. Okay, so let's take a look at this in a little bit more detail. Basically, the front processor, this is an instance of slipstreaming in my opinion, except it's a very different implementation. The front processor runs faster by invalidating long latency cache missing loads, just like in run-ahead execution. Load misses and their dependents are invalidated. Remember the invalid bits or bogus bits. Branch mispredictions that are dependent on cache misses cannot be resolved. Okay? So this leads to highly accurate execution, as independent operations are not affected. Right? Independent operations can be executed in the front processor. They lead to accurate prefetches to warm up the caches, and they lead to correctly resolved misindependent branch mispredictions. So if there's a branch misprediction that's not independent of a long latency cache miss whose data is not available, then these mispredictions can be resolved and communicated to the back processor through the result queue. Misdependents, you don't want to stall on them. That's how the front processor gets ahead. Back processor, on the other hand, re-executes every single instruction that's coming from the front processor to ensure correctness and to provide precise program states. So it basically executes instructions that are dependent on misses, and also resolves branch mispredictions that are dependent on long latency cache misses. And once that branch misprediction is resolved, the entire system, starting from the fetch unit of the front processor, is redirected such that you start from the right point. So the pipeline, the branch misprediction latency, is actually longer than the pipelines of these two cores plus the result queue. So back processor makes faster progress with help from the front processor because it gets a highly accurate instruction stream. All of the branches that are independent of misses are resolved. And it gets warmed up data caches, right? This is nice. Warmed up data caches are basically the benefit of run-ahead execution, right? Okay. Uh-oh. Yeah, I don't know what happened here, but Looks like we're stuck somehow. Let's see if we can fix this problem somehow.